today we are going to discuss how to select various change gears for changing various parameters of the machine, especially it is all related to process parameters. So, first thing, twist gear. We all know that twist is an important parameter for roving, and we need to change twist time to time depending upon the count of roving that we want to produce or the fiber type of fiber that we want to process. So, depending upon count and fiber in terms of their length or fineness, we need to change the twist. So, therefore, there has to be some mechanism to change the twist on the machine. So, how to do that? Twist, we all know that is the ratio of flyer speed and delivery rate by the machines. These two are important for deciding the twist level in a roving. If this is the ratio of these two, therefore, it can be changed either by changing flyer speed or by delivery rate. But usually what we do? We change delivery rate, as flyer speed will affect roving tension and thereby it can affect the breakage part also. So, once we choose a flyer speed, generally we do not want to change it unless there is a specific need for that, but if we want to then adjust twist, we generally adjust it by manipulating delivery rate, which obviously can affect my productivity to some extent. The twist change wheel or twist change gear, whatever we say, must be a wheel which will not change flyer speed, but change only the delivery rate and bobbin speed. So, this wheel or this gear should therefore change the speed of the delivery rate, that is speed of delivery, or at the same time the speed of the bobbin, because if the delivery changes, I have to now need to wind less length of roving, and hence the bobbin speed immediately needs to be adjusted as well. So, bobbin speed and delivery rate are connected through the winding equation. So, you can remember the winding equation, you will find that delivery rate and the bobbin speed are basically interconnected. Now, if we study the gearing plan of the machine, then how to identify which gear is going to act as a twist change gear? The designer of the drive part of the machine has given this flexibility so that twist can be easily changed. Now, one can identify the gear if he studies the gearing plan a little carefully and objectively. Now, in this machine, the gearing plan that we have in front of us on the right hand side, we see that the gear D, if we look at gear D, then we will see that this will change the speed of all elements except the flyer. Now, the motion goes from the motor, we have already started the motion flow. So, the motor is here, from here it goes there on the motor pulley to the machine pulley, and this particular shaft which is running across the full length of the machine is on the other end of this shaft. There is a wheel here, and then there is another set of gear D and G, a compound gear DG. So, the gear D, if we let us say change the number of teeth in this gear, it will change the speed of the front roller, because from here the motion through this gear goes towards the drafting system, and therefore, any change in the teeth of the gear D, G or H will always affect the speed of delivery. Any of these actually theoretically can affect the speed of delivery. However, even though delivery speed changes, the draft is not going to change, because the motion first goes to the drafting roller, front drafting roller, and from drafting roller it goes to the rest of the rollers, and therefore, the relative speed of middle and back roller, front and back roller is not going to change. The speed of all the rollers are going to change simultaneously by the same amount, and hence draft will remain same, but the delivery is going to be different. So, theoretically actually gear D, H and G all can work as a twist wheel, but because the wheel D is visible from outside, we generally use gear D as a twist change gear. This gear will also going to change the speed of the top cone drum, and that speed change would basically means, as we have studied it earlier, the top cone drum speed will affect the bottom cone drum speed, and from there through set of gears and differential gear the motion goes to the bobbin, and therefore, the bobbin speed is also going to change, because we need to change both. The delivery changes, I have to also wind the same amount of roving, and therefore, we have to identify a gear which will change both the bobbin speed as well as the delivery rate without changing the speed of spindle or the speed of the or the drafts, and hence the gear D is generally used as a twist change gear. But as I have said, in case it is necessary, gear H also can be changed, but generally the way the manufacturer has designed the machine, that the gear D is easily accessible from outside, and therefore, this gear can be easily changed to change the twist. Okay. From there we go to the next thing that we need to change time to time on the machine, which is draft. Sometimes we have to produce a finer roving, sometimes we have to produce a coarser roving, sometimes the hank or the linear density of the sliver is going to change. So, we need to adjust the draft many a times, and therefore, in the drive design this flexibility is there, that we can easily change the draft of the machine in order to produce a roving of required fineness or required linear density or hank, whatever we say. Now, if we look at this particular gearing diagram, which is shown, the various gears which are meshing with each other and their respective teeths are also shown. This is shown for a system where there are 3 pair of rollers. Now, what is going to be the draft? We have to remember the definition of draft, which we already know. So, for the calculation purpose, what we can do? We can easily find out the draft by taking that if the front roller rotates by 1 revolution, how many revolution the back roller is going to rotate, and for 1 revolution of the front roller, what is going to be the linear delivery, and for 1 revolution of the front roller, what is the corresponding revolution of the back roller if we find out, and that if we multiply it by the circumference of the roller, we will also find how much is going to be the feed by the back rollers, and that is what exactly has been done by this here. draft has been shown to be pi into 32 into 1, 32 is the diameter of the front roller, revolution has been chosen to be 1. Therefore, if the front roller turns by 1 revolution, the length of roving that we delivered is pi into 32 into 1. And for 1 revolution of the front roller, the corresponding revolution of the back roller is going to be 1 into 20 by 84, then the DCP, whatever teeth will be coming, this particular gear has been shown to be a DCP, that is draft change pinion or draft change gear, divided by 110, and then that becomes the speed of the back roller. I multiplied, that is not speed, that becomes the number of turns by which the back roller rotates, and that is multiplied by its circumference, which is pi into 32. In this case, both front and the back rollers are exactly same in terms of diameter. So, if I find out this, this will give me the draft. I may not need to know the rotational speed of the gears. Without knowing the rotational speed or without starting from the motor, we can easily find out the draft also, if we have the gearing plan of the drafting unit only. So, if I go by this, then you will find the draft is going to be a constant 462 by DCP, where DCP is the draft change pinion. So, the numerator part 462 is known as draft constant, because that is basically the value of 84 into 110 by 20. These gears are not going to change, they remain fixed all in this particular case, and therefore, this value 84 into 110 by 20, that gives you the value 462, and we call this figure as draft constant. So, draft constant becomes 462, and hence draft is always draft constant by DCP in this particular drafting system, or DCP could be draft constant by draft. Generally, what we do in the mill practices, we note down the draft constant, and it is always used to find out what should be the DCP for a given value of draft. How much draft I require, that we can find it out, what is the sliver count I am feeding and what is the roving count I have to produce. So, based on the requirement of the roving count and the sliver hang that is available, we can find out how much draft is required, and to get that draft on the machine, we will divide the draft constant by the draft that we need, and that will give me the number of teeth of the draft change pinion. That is how we will be able to find out the teeth that we require in the draft change pinion, and that is the gear is shown here. And if you look at this gear, you will find this gear is going to change the speed of which rollers? The red color gear known as DCP, if we want to make it bigger or smaller, it is going to change the speed of which rollers? Both back and middle roller by same proportion. What does it mean? That means there is no change in draft between back and middle. It will only change the draft between front and middle. So, this gear therefore, will only change the draft between front and middle, and it will not affect the draft between middle and back, which we call brake draft, because brake draft is quite sensitive to the quality of the roving. Therefore, many a times when total draft has to be changed, we do not touch the brake draft, but we generally increase or decrease the draft in the front zone. That is the usual practice. And if we need to change the brake draft, then we have to find out what is the brake draft between middle and back rollers. We follow the same logic and we only concentrate on few gears only here. We only concentrate on those gears which are connecting the back roller and middle roller. Rest of the gears we can ignore. And then we can similar way we can go for one revolution of the middle roller. How many revolution will be there for the back roller? And for one revolution middle roller, how much roving is going to be delivered, and for one revolution the middle roller, how much roving is going to be fed by the back roller. So, if we follow the same logic, we will find out this is going to be brake draft is going to be as shown in this slide, pi into 32 into 1 divided by 41 by BDCP. BDCP stands for brake draft change pinion, into 32 by 52 into pi into 32, or pi into 32 is basically the circumference. So, this if we want to simplify, this will give you a figure 0.0396 into BDCP. That means, brake draft is equal to a constant 0.0396, which we can write as 0.04 also, into the number of teeth in the brake draft change pinion, which is shown here by the blue colored gear. So, therefore, whatever brake draft we need, I can find it out if I know the BDCP, or if I want to find out BDCP, then BDCP is going to be how much? Is going to be brake draft that is required divided by 0.0396. That will give me the number of teeth that we need in the brake draft change pinion. Typical values are shown here. DCP values varies between 25 to 80 T, whereas BDCP values varies between 26 to 29 T. So, that is how in some drafting system the exact the connection between the gears may vary from manufacturer to manufacturer, and a typical case is shown here, and you can study the gearing design of other machine manufacturers and also work out the draft and the brake draft values for that particular machine, or you can calculate the draft constant or brake draft constant also. What else we need to change? So, twist and then your draft. The other thing that we need to change on a roving frame is the lift. That is, we may need to change the traverse rate of the bobbin rail. As we already know that bobbin rail keeps moving up and down, and the velocity of the bobbin rail also needs to be adjusted in order to get the right coil spacing on the bobbin. And therefore, the gear that helps me in changing this is also known as lifter change gear. It will change the speed or the velocity of the bobbin rail. So, the gear, if you look at the diagram, the gearing plan of the machine here, then we see that this must be a gear which will be able to change the velocity of the bobbin rail, and bobbin rail speed, velocity or speed, whatever I say, keeps changing. For one particular stroke it remains constant. Then once one layer is formed and you go for formation of the next layer on the top of the previous layer, then the velocity of the rail has to change. So, the velocity of the bobbin rail has to change continuously from the first layer formation to the last layer formation on the bobbin. Why? because bobbin diameter is gradually becoming larger and larger, and therefore, I need a longer length of roving to make one coil around the roving, around the bobbin. So, therefore, I have to move the rail at a slower speed when the bobbin is becoming larger in diameter. Therefore, if there is a need to change the velocity on the bobbin rail, that means its drive must originate from the driven cone drum side. Therefore, the bobbin to this part of the machine must originate from the bottom cone drum, which is a driven cone drum, and as the cone belt shifts on it, the speed of the bottom drum keeps on changing, and hence the speed of the bobbin rail will also change. So, in this diagram, the lifter change wheel is the wheel W. This wheel or these gears would be such that the coils laid hide the bobbin surface. I mean, we must lay the coils, the roving will be laid in the form of coils after coils. So, these coils should be laid in such a manner that the bobbin surface gets completely hidden. There is not too much of space between the coils, neither the coils should override each other. Both are detrimental, and therefore, initially one has to make sure that the very first layer when it is built, the bobbin surface is completely covered with the roving, but that at the same time the roving coils should not override each other. Gear E and F can also change the coil density. Coil density basically means coils per inch. How many coils I am generating per inch of the bobbin, as they can also change the bobbin speed. See here, if I concentrate on this side of the gear, theoretically W, E, F, all of them can change the velocity, because ultimately from there the motion goes to the bevel gears, from the bevel gears it goes to the bobbin rail, which we have already discussed earlier. You have to remember the motion transmission path starting from the motor to the bobbin rail. If we trace that path, and in that path the gears W, E and F are coming, as well as the bevel gears are also coming. So, the bevel gears which you see here, all these gears we keep it constant, we do not change them. Once we have decided, then we do not change. Machine manufacturer decided what should be the teeth of this gear, and they had kept it, and there is no need to change them. So, the flexibility is there in changing the gear W in general, but at times we may also change the gear E and F, remembering that E is a driver gear. If we happen to change E, is a driver gear. Similarly, W is also a driver gear. So, more the teeth of W or more the teeth of E basically would mean it will increase the velocity of the traverse. Whereas, if I choose gear F, in that case what will happen? It will decrease the speed of the bobbin rail, because it is basically a driven gear in this particular set. Okay. From there we move to another interesting part, that is relationship between lifter change gear and roving count. Let us look at this now. What is the relationship between lifter change gear and roving count? There is many a times what happens that I am producing a particular roving, let us say roving of 1.2 NE. Then there was a need to switch over to produce a roving of 1 NE. So, now the roving has become little coarser. Earlier it was 1.2 NE, now it is 1.0 NE. So, now in this case we have to quickly find out whether the same lifter change pinion or lifter change gear is going to work or not, and if not, possibly it will not work because the roving has become now little coarser. So, we need to change the lifter change gear, and therefore, we need to find out that if the previous gear was perfect for 1.2 NE, what should be the new gear for 1 NE. So, how to find out this? Let us look at this now. The traverse rate of the bobbin rail VBR is going to be how much? Ideally should be small v by pi dB into dr, where small v is the delivery rate and dB is the bobbin diameter. So, delivery rate and bobbin diameter multiplied by pi is the bobbin circumference. So, v by pi dB is actually representing how many coils I have to make per unit time, and that multiplied by dr, if dr is the roving diameter, then if there are so many coils I have to make, so the total length that the coils is going to cover is going to be v by pi dB into dr. Therefore, that is what exactly has to be the traverse rate of the bobbin rail. So, VBR therefore becomes v by pi dB into dr. Now, VBR therefore, we can write is proportional to dr by dB, because v is going to be kept constant. So, it basically depends proportional to dr by dB. Now, for a given diameter, if the dB is constant, then you can say VBR is actually directly proportional to dr, that is the roving diameter. It is also be inversely proportional to bobbin diameter. So, when the bobbin diameter grows, that is why we need to change the traverse rate, because if dB increases, VBR has to go down. But for the we are interested about the roving count now, and therefore, VBR is proportional to dr. Now, VBR is proportional to also NLCP, where NLCP is the teeth in the lifter change pinion, because I see lifter change pinion is a drive gear. Because it is drive gear, the more the teeth, more is going to the VBR. Therefore, we can say that VBR is directly proportional to NLCP. LCP stands for lifter change pinion, and N stands for number of teeth in it. So, both are proportional. Therefore, NLCP should be proportional to dr, that is diameter of the roving, and roving diameter in turn is inversely proportional to roving count. RNE is the count of roving in any system, that is English system. So, dr is proportional to 1 upon RNE, which is equation number 4, and therefore, what we can write, NLCP should be inversely proportional to 1 upon root RNE, that is the roving count. It should be the number of teeth in the change gear or change pinion should be inversely proportional to number of teeth in the change pinion should be inversely proportional to square root of roving hank or roving count expressed in NE. From there we can write, therefore, NLCP is going to be some constant k by root over RNE, and hence NLCP into root over RNE is going to be constant always. For a given type of fiber, we can say for cotton, if the mixing is not changed, this will remain constant. And if it is constant, therefore, what we will write, present NLCP into present roving count root over is going to be the required NLCP into new roving count, because this will be always equal to k. So, we can write this, and from there we can write, therefore, we are interested what is going to be my required NLCP, required number of teeth in the lifter change pinion. So, that is going to be present number of teeth in the lifter change pinion into square root of ratio of present roving count in any divided by required roving count into any. But if I follow this formula, I can always easily find out how much teeth I need in the lifter change pinion whenever I am changing from one count to another count, especially when the fiber is same. That is, if it is cotton, then it is only cotton. If it is polyester, it should be always polyester. But if you switch from cotton to polyester, then this formula may not work because of other reasons, because density of polyester and cotton are not same. The packing of fibers in roving for cotton and polyester may not be same, and therefore, this formula whenever we have to use it, we use it for when you use for 100% cotton, or we are going for 100% polyester, or if it is PC polyester cotton, then we go for 100% polyester cotton. Then formula can be used and for to find out required NLCP. Okay. The other change wheel that is required is cone drum speed change wheel. Cone drum speed, that is basically the top cone drum speed and bottom cone drum speed, these two speeds are there, two cone drums are there, and cone drum speeds can be changed by the wheel K. When you need to change it, let us look at this first. Now, if the diameter of the bobbin tube is changed, the speed of the bobbin has to be changed. This can be achieved by two ways: by shifting the initial position of the belt on the cone drum, or by choosing appropriate teeth in wheel K. Now, if we look at the wheel K, what wheel K is going to do? Now, wheel K is feeding motion to through this set of gears, it is feeding motion to the differential gear, and also motion is going from this side to the bobbin rail. So, the gear K will affect the speed. Therefore, if it go through the differential, then the output of the differential goes to the finally to the bobbin. So, it is going to change the speed of the bobbin. Therefore, this wheel is going to change actually the speed of the bobbin when we need to change the tube diameter of the bobbin, that is the diameter of the bare bobbin. When there is nothing on it, diameter of the bare bobbin has been changed due to some reason. In that case, I have to run the bobbin at an appropriate speed, so that I can wind the roving that I am delivering. So, this wheel is not going to change the speed of the cone drum, but is going to change the speed of the bobbin. Depending upon if I go for higher value of K, the bobbin speed is going to increase. If I go for lower value of K, the bobbin speed is going to decrease, because the additional speed that it is feeding to the differential depends upon the value of K. So, sometimes we need to do it, especially when we are switching from one particular diameter of bare bobbin to another particular diameter of bare bobbin. Sometimes we may increase the diameter due to some reason, sometimes we may decrease the diameter due to some reason. So, the diameter is decreased, then we have to go for a little higher speed of the bobbin, because delivery is supposed still remain same, diameter has decreased, I have to go for higher winding speed to wind the same delivery. And if how do I increase the winding speed? Flyer speed is constant, that does not change. So, the speed difference between flyer or bobbin and flyer is what is winding speed. So, therefore, I need to now this case when the bobbin diameter is less, I have to increase the speed of the bobbin, and therefore, I have to feed more speed to the differential through the gear K. So, gear K is used for such purpose. So, the other thing is, this is another gearing diagram for the retard machine, and this is also a very popular company. And if we look at the gearing diagram, we see in this modern machine there are how many motors are there? There are M1, M2, M3, M4. Whole machine is actually run by 4 different motors. Motor M4 is exclusively driving the drafting unit. It is independent of rest of the motors. It is only controlling the speed of the drafting rollers and the rollers which are there in the creel part. M3 drives the bobbin rail. So, if you look at the M3, it is only affecting the speed of the bobbin rail. Motor 2 drives bobbin through differential gear, which is motor 2 is here, it is driving the bobbin through differential gear. Through this set of gears, it is driving the bobbin, and motor 1 drives the flyer only. So, today the most modern machine, this is what is going to happen, that we have multiple motors, and these motors are driving different parts of the machine, and therefore, they can be independently controlled whenever we need, but they have to work in such a way that there should not be too much delay in their starting the motor. There is a they have to work in such a way that the timings of their starting has to be highly synchronized. The PS in this case is the draft change gear, PS1 shown here as to brake draft change gear, that is here, TS is the creel tension draft gear. So, here separately we can study the drafting unit with same procedure we can follow, and we can find out what are the speeds of the different rollers, and we can calculate what is the draft the different draft in different zones. Also we can find out what is the speed of the flyer or what is the speed of the bobbin. So, calculations can be done in a very similar manner, provided we know the motor speed and the diameter of the motor pulleys. Now, we come to the production calculations. Now, production based on front load delivery and roving hang given in text. Expressing roving hang in text means the calculation will be a little bit simpler. When you express it in terms of NA, the calculation becomes not difficult, but I should not say really difficult, but the little difficult than this one when you use in text form. In text it becomes very direct and very fast we can calculate. So, production per spindle in kg per hour we need to calculate. So, we need to do what is the front load delivery rate, that multiplied by 60 will give you the delivery in 1 hour, that divided by 1000 will give you, no, first of all let us say delivery in meter we are getting, multiplied by 60 will give you delivery in 1 hour. And if we know the roving hang in text, then basically means that if the text is whatever is the value, about it is x, then basically what does it mean? That 1000 meter will weigh x gram. So, if there are so many meters are there, so we can find out what is going to be the weight per gram, and therefore, what is going to be the total weight of the length of roving that we are producing. And that divided by 1000 is basically giving converting gram into kg. So, denominator the 1000 figure that we get, that is to convert the weight that we get in gram into kg, that multiplied by efficiency factor depending upon what is the efficiency of the machine. So, the machine has to be efficiency has to be given, then we can calculate what is going to be the production per spindle in kg per hour. Roving hang in text basically means weight of 1 meter roving in gram. So, 1000 in denominator changes the unit from gram to kg. The other thing is production based on spindle speed and roving hang. So, earlier it was based on front roller delivery and roving hang. Now, let us say I am interested, I do not know the delivery rate, but I only remember the what is the spindle speed and what is the roving hang. Based on that, if I want to calculate, then we have to first find out, ultimately we have to first find out what is the delivery rate. So, delivery rate is spindle speed by twist. That means we need to know what is the twist in the roving now. Knowing the twist, we can find out the delivery rate, and therefore, production per spindle in kg per hour is going to be spindle speed by twist into 36 multiplied by 60 into 453.6 divided by roving hang in any in this case into 840, and that multiplied by 1 upon 1000 to convert it into kg and multiplied by the efficiency value. That will give me the production per spindle in kg per hour. And if I simplify this, I will get this figure 0.9 spindle speed by twist into 1 upon roving hang into the efficiency part, and we get a figure 1000 into 100. So, we get 100,000 in the denominator, and this will give you the productions per spindle in kg per hour. So, therefore, we need to know in this case spindle speed or flat speed, both are same. We also need to know what is the twist in the roving and what is the roving hang and what is the value of efficiency factor. So, we need to know 1, 2, 3, 4 parameters to find out the expected production or actual production. This is all basically estimated production. Actual production, if you want to know, we actually weigh the bobbins and find it out. That is what is actual production. We have to know what is the weight of the bare bobbin, what is the total weight of n number of bobbins, and then you subtract the weight of n bare bobbins, you get actual production, but these are all basically estimated production. As an example, we are showing one particular example here. Spindle speed is 1100 rpm, roving twist is 1.25 TPI, and roving hang is 0.95 NE, efficiency is 80%. We need to find out the production per 8 hour from the following data. So, if you look back the equations that we have stated, delivery for 8 hours, we first try to find out spindle speed by twist in 36, 16 to 8, this gives you a value this much. That means per 8 hour per spindle we are actually delivering 11,733 yard of roving. So, production of 8 hour will be the weight of 11,733 yard of roving of 0.95 hang, and this figure if you work it out, it will give you a value 5.33 kg per 8 hour. That is going to be the production. The other thing is how to calculate the volume of a roving package. So, a roving package geometry is shown on the right hand side. Now, the roving, we can see it that it has basically an upper part, a lower part and a middle part. So, middle part is perfectly circular, just like a cylinder, it is a hollow cylinder. The top and the bottom part are basically conical in nature. So, if we have to find out the volume of this package, then how to find it out? Let us consider the conical end of the package first. So, this conical end is being shown here. Now, what we see here that let us now look at these two similar triangles OAB and OCD. If you look at these triangles, then what we can write, AB by CD equal to OB by OC, by because they are similar triangles. Triangle OAB and triangle OCD are similar, and therefore, AB by CD is going to be OB by OC. This is simple geometry, and we write the values of AB and CD, and we can write therefore, H by L is going to be dB by 2 divided by dB minus B by 2. If you study the figure carefully, you will find that this is obvious, and from there we can find out what is the value of H. So, H is giving me, first of all we find out what is the value of H. Okay. So, what is H? Look at this, it is the value of AB. So, that is the value of H. Now, we go to the next page or next slide. What we have to do? The value of the volume of roving in the conical part, first we want to calculate. In this conical part, the bottom part and top part are basically exactly same. So, we are concentrating on only one part first, and the bottom part which is going to be the same. So, if you look at the top part, then the volume of this cone in which we are interested, that is roving, which is there, that will be volume of the entire cone OAE minus volume of the cone, this top part, this volume is there, roving does not exist. So, this we have to subtract, and we have to subtract the volume of the cylinder, that is we have to subtract this part also. Then we can find out what is the volume of the roving in it. So, basically we are trying to find out volume of the cone OAE minus volume of this cone, small cone on the top, minus volume of the cylinder, which is basically the bobbin, the bare bobbin. So, volume of the cone OAE is standard formula 1 upon 12 pi d square b into h, where h is the height of the cone and dB is the width of the base. So, this bigger cone, the volume is 1 upon 12 pi d square b into h. The smaller cone on the top part is 1 upon 12 pi small b square into h minus L, because the height here is only this much, this is h minus L, and the volume of this cylinder is going to be how much, pi b squared by 4 into L, or b is the diameter of it. It is a cylinder, the volume of a cylinder is pi d squared by 4 into L. So, this is what we have written it here, and then we are actually going for simplifications of this expression. So, if we simplify it, we get equation number 2. Now, substituting H in this equation from the previous equation, if we substitute the value of H here, then we will get what the steps which are shown here. One has to, you can do it yourself, and if we go by this simplification, we will get this figure. So, what we do is this, that this is the final result, this should not be here. In this previous equation, we put the value of H, and we keep on doing the simplification part. We arrive at this particular equation which is shown here, that is V1 is going to be pi L 12 by 12 into dB minus b into dB cube minus 3 dB into b square plus 2b cube. This is the simplified formula of this expression So, that gives you basically the volume of the top cone, top conical part. So, volume of the top and bottom conical part are same. So, we need not to calculate the same expression we can use for the bottom part also, and the volume of the cylindrical part where the roving is there is going to be how much? This is going to be, that is basically it can imagine it to be two cylinders, one big cylinder, one small cylinder, and therefore, the bigger cylinder volume is pi dB square d square b by 4, the smaller one is pi b square by 4 into h, both are multiplied by h. I can take h common and write this figure, and therefore, it is going to be pi h by 4 d square b minus b square, that is the volume of roving contained in this middle part of the bobbin. Therefore, the total volume of roving is going to be 2 into V 1 plus V 2, and if we go by this, we get this expression number 5. Is a little lengthy expression, and if we know the complete geometry of the bobbin, parameters like h, d b, small b, l, then we can find out the total volume of roving that we have in the bobbin. Now, the another interesting part is the roving diameter within the bobbin. See, roving is a very compressible material, no? It is because too much of twist is not there. So, it is difficult to know what is the exact diameter of the roving, and when the roving is wound on the bobbin, it remains compressed, because I am winding it, there are so many layers, one on the top of the other. So, the top layers are compressing the middle layers, the between layers are compressing the bottom layers. So, therefore, the rovings are in compressed state, and if we want to know what is the average roving diameter within the bobbin, then we can find it out following this method. Let us assume the roving is to be round within the bobbin. This itself, this is an assumption which may not be correct, but to make the case simple, we say this is the true, that is less round. The roving count is assumed to be C in terms of text. Average roving diameter, let us say DRC in a compressed state. So, this DRC roving diameter in compressed state within the roving bobbin. Weight of the bare bobbin is small w, weight of the full bobbin is capital W. So, the roving content is W minus small w in terms of gram. Now, if I know the weight of roving, then I know the roving count in text, which is C, I have written it here, that the total length of roving in that roving bobbin can be shown to be 1000 by C into W, capital W minus small w. This will give you the weight of the length of the roving in meter. So, C by 1000 is basically, see, the count is C text. So, 1000 meter weigh C gram, therefore, C by 1000 this is the weight of 1 meter, C by 1000. I have W minus W gram, we have to divide W minus W by C by 1000, that will give me the length of roving in meter, and I get therefore, this expression LR, length of roving, is going to be 1000 by C into capital W minus small w. So, volume of the roving of length LR, this roving, what is the volume of it? If the roving is considered to be circular with an average diameter DRC in compressed state, then pi d square by 4 divided by 1000 into 1000 into LR is going to be the roving diameter in millimeter. This is will be the diameter, considering the DRC is basically diameter in millimeter. Then this 1000 and 1000, these two figures will come into denominator. Now, this is if this is the volume of the roving, equating the volume of roving estimated on the basis of weight with the volume estimated by actual measurement of dimensional parameters of the full bobbin. So, full bobbin, the geometrical parameters we know, we calculate how much is the volume of roving which is there, and we also calculate the volume based on the weight, and you equate these two. If we do it, then we can find out what is the diameter in the on an average diameter in a compressed state, and that figure will give you this value. DRC is going to be finally 1128.38 root over VR by LR in terms of millimeter. This is in terms of millimeter. That means DRC finally I get it in terms of millimeter. So, therefore, we can say the average diameter of the roving within the bobbin on an average is going to be a constant multiplied by root over VR by LR, where VR stands for what? Total volume of roving, and LR stands for total length of roving. And these two parameters we have to estimate based on weight and the dimensional parameters of the roving bobbin. Then we can have some idea how much is the average diameter of the roving within the roving bobbin. Let us see a small video clip of the machine. We are first showing the creel part of the machine. So, here there are so many cans behind the machine. You see the slivers are being lifted, they are passing over the guide pulleys, and this part is the back of the machine, and the slivers are going to the drafting unit. The cans are arranged in 4 different rows, and you see the way the sliver is lifted. Sliver is lifted at a very, very slow speed. The speed of the back roller is how much it could be. The delivery rate of this machine typically could be 15 meters per minute, and the back roller could be 10 times less. The next video क्यों नहीं होता ये? अच्छा, now let us see this flyer is turning. You can see the way the roving is being wound and getting twisted. From front roller, you see the drafted sliver is moving out. Part of the creel is also visible now. You can also see the false twisters at the top of the flyer. They are putting additional false twist so as to strengthen the roving. Okay. With this, we close this particular discussion now, and thanks now.